All right, let's go ahead and get started. So, yeah, so sorry about missing stuff last week. I still not 100%. I haven't had a chance to look through the assignment fours. I've just gotten started. I mostly looks like people have turned them in at least, but I haven't looked at them past that, but I'll try and get those here as usual. Maybe we'll talk about those a little bit on Thursday if there's any issues or things to review on the assignment four. So my plan is probably to keep it relatively short today, but we'll get started on the decision trees and maybe bring up there is assignment five as usual. So just looking ahead for people watching this. Our next two units are going to be our last ones where we're going to be talking about supervised learning. So we're going to look at ensembles. Well, we're going to look at decision trees this week mostly. And then we'll look at more general the idea of what we mean by an ensemble. So, and there is a usual assignment, which is over building some ensembles by hand, and a couple of things that we'll get into next week about different ways that you can actually sort of build an ensemble. So an ensemble, just to get started on the material here for this unit, is really just a collection. So the idea is that sometimes you can actually get an improvement on your model or your predictions by having multiple things that are making a decision. Okay, and so by combining their decisions, you'll get a better predictor than just an individual one. Okay, so and some of the most basic ones. Most basic ensemble is to collect together a bunch of what are known as decision trees. Okay, so but yeah, so I am jumping ahead a little bit. So we're gonna start with decision trees this week for the most part. So that should be the notebook that's numbered Unit 11 here. So give me a second. Let me go ahead and bring up our decision tree notebook. I'll probably spend most of the rest of the time looking at the decision trees. Maybe I'll bring up the ensemble assignment a little bit real quickly as well at the end of class here, just to get started on that. So, also don't forget about the class projects. So hopefully everybody continue to make progress on those and looking at those. So I had something about that, but anyway, so I'll try and continue to at least mention that, remind people about that. I haven't looked at those. I'll just make a kind of another reminder that it is a good idea to be doing stuff weekly on those. I'll probably have that at least as a little part of my evaluation, that it looked like you were actually doing commits regularly, and we're actually making incremental progress rather than just doing it all in an hour at the last week or two or something like that. So, all right. So let me go ahead. Let's bring up the decision tree notebook here. So, looking at this week's material, Dr. Ng, I've been recommending people look through Dr. Ng's lecture stuff, but he doesn't really have any materials on decision trees. So this week it's all just there is a video going over the decision tree, basically the same notebook I'm probably going to be talking about here today as well. But I do have a kind of a canned video on this material. I do need to update some of these things. So right, we are really working through all this material is coming directly from the Chapter 6 hands-on machine learning or textbook on decision trees and things. So, all right, go ahead and bring up the notebook. So yeah, I really only have like kind of one notebook for this week and then one notebook for next week. Although there is some overlap on this notebook with the like official repository notebook for the class. Maybe that kind of one last reminder on things. So I don't know if I've mentioned this before, but there is another resource that is useful. I do recommend maybe people also look through that. So sometimes some of the lecture notebooks that I have, especially these last couple of weeks, probably there'll be quite a bit of overlap. I mostly took a lot of material from our hands-on machine learning, but all the examples in the textbook for the hands-on machine learning, they actually do have GitHub repository, so there's links to those and the additional resources. So those notebooks are really pretty much there's not a whole lot of discussion in there. They kind of expect you to be reading along on the textbook. It's really just the code examples for the most part, but those can be useful as well to look through those if you have problems like going through the official textbook and entering in the code yourself. You can sometimes, and there's usually some additional kind of things, some additional stuff that you don't get in the textbook in the official repository for the hands-on machine learning. So, let's get into decision trees. I won't spend too much time on this one. Decision trees are this is actually another example of a method that it's really quite a bit different. It's not the same as kind of the default linear logistic regression way of building a model. Okay, so it's another example. So last week, the two that we looked at also were kind of different. So we are spending these previous 2 or 3 weeks on looking at some different ways of building supervised learning mechanisms that aren't in the same kind of mold as the basic support vector machines, linear logistic regression, the idea of fitting a set of parameters. So for decision trees are another one that a lot of people, a lot of students find this is pretty intuitive, and it's pretty easy to implement the basics of a decision tree by hand once you understand the idea. Okay, so a decision tree, if I jump ahead to it, if you haven't done the reading, oh shoot, what happened to my nice figures on this thing here? So there are some figures, they're not showing up here though. So there might be some dead links in this notebook. The link for the figures looks like it's wrong in here, so it should have just been one directory up from the current location. So I guess I might not have checked this out in a while. See if I can get that in there. So I'll come up to generating these in a bit here. Shoot. That's not working. I'm going to have to rerun the notebook to get those. So we should have these figures in here though. Yeah, I guess it's just not generated. So let me try rerunning this notebook here real quickly. At least down to that point here, so I can see if I can get those. So here, just to mention a little bit about this, I guess it is described in this lecture notebook if you haven't done this, but if you want to actually run this command to generate the figure, I thought the PNG should have been in the repository. It might not be there, so you might not. The same thing that I'm having an issue here of seeing these figures. You might not see it. Oh yeah, so it looks like I'm gonna have to do this step here real quickly. So let me install this graph viz and kind of show you doing that. So if you're using our environment and if you're reopened in the container, it is a Linux Ubuntu kind of environment, so you should be able to do the regular package manage stuff, including to get this external package that's used in these examples to generate the figures for our decision trees here. So it's I thought you could get it from apt install. Let me try it one more time. Did I mistype that? Yeah, I probably mistyped that. Yeah. So you should be able to do like an apt install of the package here, and then hopefully that'll allow us to actually run our thing here to generate the figure. So this first one just exports a file in this particular format that's used by this GraphViz tool. Yeah, if you install this, you can do this by hand, but you can also do this programmatically if we have the right file. So we might have to also do a we might have to install it at the Python package as well, which looks like I didn't have a description of that either. So it's probably the Python 3 GraphViz. I don't know if I did that too quickly. So there's two separate things. So there's the basic tools on the Unix Linux the GraphViz, but there's also a Python package. So for most recent versions of Ubuntu kinds of things, if you want to get a particular Python package installed, it's usually something like Python 3 dash the name of it. That should allow us to, if we're in Python, to import the Python GraphViz. Just check it out. Nope, that didn't work. So let me try installing it from Conda. Oops. So yeah, apologies, I didn't get a chance to check this out beforehand. So it looks like a couple of things might be missing from the notebook that if people were interested in seeing these visualizations here. I'll have to update the repository, but so when you install stuff from Conda, usually you don't have that Python 3 dash in front of the package name. So I'll show this again, but I was trying to install the Python package for the GraphViz. I was just using Conda, which is a Python package manager that we're using in the environments for our class setup. So that's the another place where you can get packages from using the Conda package manager. So let me see if shoot. Okay, none of those are getting it for me. just real quickly check it in my notebook here, but I might have to go back and do this later. Okay, anyway, I'll come back to that. I'll try and fix this before Thursday, just so people can use them. Let me check if there's a command line tool, but again, this will only work if you're in an environment where this tools have been installed. So also, it looks like the path hasn't been updated on this here, so we want to go up one directory. There we go. I think I finally got the PNG here. Yeah, there we go. All right. So anyway, there's one method. I'll come back and fix that, but this GraphViz tool, if you're interested, if you are using the environment for our class, the apt install should work when you're running inside the dev container, and that will allow you to use the dot tool, we should be able to install the Python package for GraphViz as well, so I'll have to figure out what the correct way is to do that. Looks like it's changed a little bit from last time I've run this notebook here. So once you do that, also these paths look like they're wrong on some of the stuff in this notebook, but once you do that, you should be able to generate these decision trees from a train. In this case, we had a train decision tree classifier from scikit-learn that was trying to visualize the tree for. So, there we go. All right. So I'll try and remember to fix that before our next class meeting. But anyway, the reason why I kind of wanted to have this up and be able to generate these in the rest of the notebook is, so I started talking about the basic idea of a decision tree is really quite simple. So most students intuitively understand what we're doing for this in order to build a classifier. In fact, if you've done the readings or if you went through this notebook, one of the big advantages about a decision tree is they're much more of a white box, I think that's the term our textbook uses, than a lot of the other machine learning mechanisms that we look at. So by that, our textbook means that they're a lot more directly understandable how it makes its decision, okay? Because the decision tree is really just, like is shown here, it's really just a set of tests that we make that always have a true or false answer. Till we either get down to a point where we're ready to make a prediction or we're going to ask further questions. So in this case, this very first example, we're using the iris dataset again. We're using just a subset of it, so we're only using 2 features so we can visualize the resulting classifier that is fit when we when we train our classifier with some of the iris data set here. And we're only using the petal length and petal width for our input features, although we're leaving it where we're predicting the 3 different classes. So we are doing a multi-class classification here for the Virginica and the Setosa and the 3rd class here. So the basic idea, the whole rest of the notebook then is figuring out the automated method that was developed in order to come up with, how does the machine decide that we first want to ask about petal length, and then if the petal length is less than 2.45, we'll give one answer, and if the petal length is greater than 2.45, we'll actually ask another question and do some further divisions here. Right? So in this case, it picked that as the feature that we were going to make a decision on, and this was the value that made the decision on that. So when it's less than that, so for this data set, the reason why I did that is it's linearly separable. The Setosa class is linearly separable from the versicolor and the virginica classes, right? So by making a decision on that feature at that value, 2.45, we could completely separate Setosa from all the others, right? And that's kind of what these things are showing inside of the visualization of the decision tree, right? So initially we had 150 samples evenly divided by the 3 different classes. And then on that particular decision, we only have 50 samples where it's true that the petal length is less than 2.45, and all 50 of those are Setosa. And then the other 100 samples, the petal length is greater than 2.45. So we have 100 samples that are evenly divided between versicolor and virginica here. Okay. And in this case, when we trained this decision tree, I skipped over it here, but one of the parameters we'd set was max depth. Okay, so we'll talk about that a bit later on here. But that basically limits the number of steps here. So the tree height ends up being 3. That's equivalent to saying that we're only going to go to a division or a decision depth of 2 here. Right? So we at most make 2 decisions before we stop dividing. Right? So anyway, to finish up this very first example, there's no, the versicolor and virginica, those 100 samples are not linearly separable on petal length and petal width. So the best that can be done at this point is to make like another division. So the decision tree algorithm picked petal width to divide by petal width less than 1.75. So 54 samples have the petal width of less than 1.75. So notice that all the samples here have a petal length greater than 2.45 and a petal width less than 1.75. That's what this leaf of this decision tree is. So, so I might not have mentioned, but it is worth mentioning. I mean, this is a binary tree. So if you know what a binary tree is, that's what a basic decision tree is. So every node is going to be split into potentially into 2 children nodes, and in this case, the paths of the decision are going to be either true or false based on some decision parameter that we make in the tree here. So anyway, yeah, this leaf node here, all the samples, the 54 samples in this, have a petal length less than 2.45 and a petal width less than 1.75. Among those, so we're not perfectly separable. So since we had to stop at a max depth of 2 here, this was kind of the best we could do. So we end up getting, all 50 of these Setosa correct in the original data that we fit our decision true. And we're going to get 49 out of the 54 versicolor, but we'll misclassify 5 of these. So 5 of these actually have petal widths, and have petal widths less than 1.75, even though they're virginica, and the same one. So on this leaf over here, these are the ones where the petal width was greater than 1.75. We had 46 of the 100 ended up over there. Among those, only 1 was a versicolor, which would be, since we're classifying stuff that ends up in this leaf as virginica, 1 would get misclassified, and then but the other 45 were the virginica class. Okay? And if we hadn't limited the depth, we could have kept doing this. So we could have split on petal length or petal width again for both of these in order to. In fact, also to skip ahead a little bit, one of the, I don't know if you consider it a good or a bad property, but a decision tree, when you fit it to a set of data, you can always overfit it. You can always, if you don't limit the depth, you can just keep dividing until there's only 1 sample left. So you can always make it perfectly classify the data you create the decision tree with. Okay? That's, of course, usually not a good idea, though. That'll be overfitting the data, and it might not do, it probably won't do well if you do something like that to make predictions on unseen data. So it's another thing that's discussed in this notebook and in the chapter 6 on decision trees here. So. Okay. Check something real quick here. Make sure this is still working. Okay. All right. So for the rest of the time, let's get into a little bit of the details of how that tree is actually created algorithmically by machine learning. So. I probably should have mentioned before I started that we are mostly talking about classification here. You can use decision trees for both classification and regression. So our textbook also talks a little bit about how you would do a decision tree to fit a regression problem. But yeah, since it's kind of a discrete. So every node in the decision tree is making a discrete true or false decision. Classification is more of a natural fit for decision trees. So we'll start with that. Probably already went through all this. This is basically what I was just discussing here. So if you have a decision tree, it's very easy for a human to understand what it's doing and to actually use it to by hand go through and make predictions on a new sample or an existing sample in order to see what the decision tree, what prediction it would make for the value here. So I wanted to, hopefully this plot is working here as well. So for that decision tree that we just fit, this is a visualization. So the decision tree is always going to make, so this is another thing that we should talk about, the boundaries that it makes are always going to be linear. But as we'll see here later on, if we will allow the depth to go on more, it will look much more complex like this than this example here. But this one is basically the decision tree that we just showed before here. So the first decision is made on whether the petal width is less than 2.45 or greater. So that gives us our first decision, which separates the Setosa from the other 100 versicolor virginica. And then the second decision on the right-hand side of that tree is happening here on the petal length, whatever it was, 1.75 or something like that, right? So again, there's no perfect, these aren't linearly separable like either of those. So we could have it might have also maybe been able to make another split on petal width instead of petal length. But yeah, choosing here, we get a few Virginicas misclassified, and there should be a few versicolor. There should be one versicolor up here, but it's probably hidden behind one of these, so we can't see it. So, but yeah, there was one misclassification when it was greater than up there. So let me discuss a little bit about this measure. To get started, I'm talking about how this decision tree is generated algorithmically. We have to understand this idea of the Gini impurity. First, it's just useful to understand, how it's calculated. Okay, so the impurity, the definition. So we give a formal definition of it right here. All it is it's the sum of the ratio of each of the classes that we had here. So for example, this is showing the calculation of the 0.168 that we got for, which one is it? For this one right here, where we ended up in this leaf node here. So we had 0, 49, and 5, okay? So what we're doing is just taking the ratio of each one of these to the number of samples. So we have 0, 54 plus 49 over 54 plus 5 over 54, right? And summing those up. Or taking the square of those and summing those up, right? And we take 1 minus the sum of the squares of those to get this Gini purity measure. Okay? So, so it's not hard to calculate that. What this is doing is it gives a measure as as the name kind of implies, the impurity in this case. It gives a measure of basically how well a particular split does. Right? So, so if we go back and look at these measures, so for example, the impurity will be 0 when you find something that's linearly separable. So when you find a decision boundary that can make a perfect decision. So in this case, everything ended up in one of the 3 classes for a multi-class classification problem, and there was nothing in the other. Right? So if you work that out, you get 50 over 50, which is 1 squared. And then these are going to both be 0, so you get 1 minus that 1 squared. That's how you get to 0, right? So small values of Gini mean usually that we have a very pure cut, a very pure decision was made. Right? So the closer to 0 you get, the better that the boundary was made. And the closer you get to 1, so on the opposite end, the closer to 1, the more mixed that resultant decision boundary is. So while this gives you a 0 on this one, the remaining things you have had it evenly split, 50-50 between the other 2 of the 3 classes there. So if you work that out, these are going to both be 1/2 squared plus 1/2 squared, which gives you 1/4 plus 1/4. Add that together, you get 1/2, and 1 minus that is still 0.5. Right? So the actual worst that you can get, so you usually can't get exactly 1. So for example, so the worst you can actually get, it would be at the very top here where we haven't done any split at all. So we've got exactly even between all 3 of the classes, gives you a 0.667. So, if you only had 2 classes, and they were exactly evenly split, you get higher. But as you progress down here, so notice for our 2 other leaf nodes, we get impurity scores better than 0.5, and the more pure it is, so the better that leaf node ended up being, the closer to 0 it ended up being. Okay? So to skip a little bit to some of the discussion that's made here, the way that the CART algorithm is the thing that's discussed in our textbook for automatically creating one of these trees. Okay, so we can turn this into a minimization problem. So just imagine that we could test all of the infinite number of divisions of the petal length and the petal width, but for every one of those, we can calculate what would be the resulting 2 leaves here. Okay, and then so for this split here, normally what is done then for the CART algorithm is we take the average. So by doing the split, we have an average of it's a weighted average. So we had 50 samples had a 0 Gini, and 100 samples had a 0.5 impurity score here. Okay? But so if you can imagine checking all the different splits of petal length and all the different splits of petal width, and then taking the average of the resulting decision there, and then you want to minimize that. So whatever gets you the smallest weighted average for a split, you would select that, okay? That's essentially what the CART algorithm does if you read here. So this is more formally doing something similar to kind of what we talked about before. So the cost function is this J here again, right? And the cost function is really just the weighted average. So again, this is just a formal way of saying we take the weighted average. So for some particular parameter k and the threshold for that parameter k, we can calculate the weighted average. So we get the Gini impurity for the left and the right split, and we take the weighted average. So however many ended up on the left-hand side divided by the total as our weighted average times the Gini, and the right-hand side for the right-hand side. And then we can try and minimize that. All right, so find the cost that has the lowest weighted average for that. That's what the CART algorithm is doing, kind of just describing it at the highest level. Although one difference, the CART algorithm is actually a greedy algorithm. So one difference, if I can go back to the tree, is what we're describing here is actually only done each node individually. Okay, so we first minimize the split at the very, when we first start creating this decision tree, we're going to pick this parameter and this threshold, presumably will give us the smallest weighted average for the two resulting nodes there. But then we keep doing that. So you can't actually get a split that's going to improve the Gini here. So once you hit 0, you'd never be able to improve, right? You can't minimize that. But anything that's non-zero, you could potentially also keep splitting that in order to get the weighted average. So 0.5 here should, the resulting split here should be less than 0.5 if you would calculate the weighted average here. So again, the weighted average would be, we have 54 of the 100 ended up on the left-hand side, so 54 100 times the 0.168 plus 46 100ths times the 0.043. Right? But yeah, that should be much less than 0.5. But anyway, the CART is really great. We could set this up as an optimization problem where we're going to minimize the Gini score over the whole tree. As is discussed here, though, there's no way for finding a global optimal tree that is algorithmically tractable. So the only known algorithms right now, if I wanted to get an overall global minimized decision tree, they are going to be NP complete, which means they're basically exponential in the number of parameters and the number of splits that we need to make on the tree there. So it's unfeasible to get a globally optimal decision tree, at least for any known algorithm right now. So in that case, so this is common. If you've done a little bit of study on algorithmic complexity, so often things that are intractable, we can still get reasonably good by using greedy algorithms. So in this case, we get things that are probably pretty close to the overall optimal tree by just minimizing for the splits and just keep repeatedly doing that until we can no longer split or until we decide to stop, like we have a max depth or some other parameter that causes us to stop. So anyway, I mean, that is an important thing to kind of understand about this. Hopefully people are kind of following what I'm saying here. So the way that the CART algorithm works, we have some measure. Conceptually, we are, when we're first deciding how we're going to split at the very beginning, this first node here, we're going to be looking at all the potential petal length and petal widths, but there are an infinite number of potential thresholds that we can split there, but we can turn that into an optimization problem. So that's not really an issue, even though there's really an infinite number of thresholds on petal length and petal width that we have to decide here. But among those, we're only looking for the one that will give us the lowest weighted average for our whatever impurity measure that we're using on the split. Once we've done that, we just continue doing that recursively until either we can't split any further. So you can end up with a place where you have a Jenny that's still, no, that's not true. You can always, the leaf nodes, if it's above 0, you will be able to split it so that you get them down to 0. So if we allow this depth to continue going on here, we'd be able to continue splitting these. So for example, this one here where we went, it was less than 1.75 on the petal width. Again, looking at our visualization here, that's the things down here. So I could then continue splitting. So for example, I might make another split here to get off those two and that. I'll just kind of do this by hand here. So our decision tree, I don't know what would be the optimal here, but it might end up being something like make another split here to get another 2 off, and then once we have this, I don't know, we might be able to do like another one here, and then among those, then I can finally get those perfectly done, and then I can have maybe another split like that to get that one out there, right? So once you get down to that, then you would have all the leaf nodes would be finally down to 0 because they're completely pure. We have all in one class and nothing left in the other. So the algorithm will eventually terminate the greedy cart algorithm. It's just doing things here. Okay. So I do think it is useful, though, to at a high level to kind of understand this measure. You can use other measures. So again, I'm probably skipping ahead. Oh yeah. So another common one besides Gini impurity is to use entropy. So you can get similar results with entropy. So I think the default for scikit-learn though is to use this Gini measure. It's a little bit easier to understand than entropy. But it's the same idea. So as long as you have some measure that gives you some idea of how pure or impure, so how well the split did, we can apply that. And it's also good to understand that this isn't a globally optimal. So this is different from the optimization that we talked about before for linear and logistic regression kinds of things. So that once you set that up, is guaranteed to find the global minimal cost function for the set of theta parameters. This one, in theory, the decision tree that you would get from doing this incrementally, greedily here, you might be able to find a decision tree that would be better in the global optimal sense if I can optimize over the whole tree at the same time. But that would take too much computation to do that for a reasonably sized problem. So it is thought, though it is, you can usually see that in practice that just doing it this greedily so doing it incrementally, you'll get something that's probably close to what the global optimal is in a much less amount of computational time, so in a much more reasonable amount of computation. So yeah, so I'm just reading over one or two more things to kind of summarize on this. So the resulting tree that's built by this method is a binary tree. So they are easy to understand. People could use. I mean, in theory, you could use this tree to make predictions by hand relatively simply. Although usually, if I have thousands of parameters and I let my tree grow to be, could easily be depth of hundreds or so. It would be tough to do something by hand like that. But in theory, you would easily be able to understand why it makes a decision if you had the resultant decision tree and how it's doing its work on making predictions for values. So yeah, and there's some other advantages. Decision trees are actually surprisingly can do well in lots of contexts. Okay, although a basic decision tree often is not going to work. It's not going to be the best kind of classifier, but collections of decision trees, so an ensemble of decision trees, can work very well. In fact, they tend to compete even with things are considered the best of algorithms for building machine learning classifiers. So, and they have some other kind of nice features. So they're not very sensitive to the scale of the data. Again, that's kind of because of the way that the algorithm works. So you don't really have to do as much data preparation, which makes them also another good method to just try as kind of a first thing, maybe like a baseline, using a simple decision tree and see what kind of performance you can get on your data set. Okay. And they are considered more intuitive. So yeah, our textbook, I mentioned this before, our textbook brings up this idea of white box versus black box. So it's another advantage of a decision tree. It's usually natural to give to understand why it made the decision that it did once you have the decision tree created. So. Kind of like the final thing so I'll leave a little bit more detail of the CART algorithm and some other stuff for Thursday. We'll probably start talking about the assignment decision trees and ensembles on Thursday as well. Maybe the last thing I'll just mention here is another nice thing about decision trees is that we can use that summary as a basic estimate of the class probabilities. So, for example, for the tree that we've been using, we know that we didn't end up with perfect, since we limited the depth to 2, we didn't end up with a perfect classifier, which usually you don't want to do. You don't want to overfit your tree and sort of perform well on unseen data. So in this case, though, we can use this basic information about what we end up with at the leaf as the probability that we would assign for our predictions. So if we end up predicting versicolor, if we're asked to assign a probability, we would say, well, there's a 49 out of 54 that percentage chance that we're correct on that. There's a we're very highly certain there's a 0.54 that it's the Setosa, but there is still a little bit of a chance that's one of the versicolors, 5/54, whatever that percentage is. So that's all that we're talking about on the estimating class probability. So that is what's used on decision trees if we want to give an idea of how certain or uncertain we are about a decision when we get down to one of these leaf nodes here. So we'll need that. So when we build ensembles, one of the things we'll do for ensembles is use a weighted, so if I have multiple classifiers, I will want the classifiers usually to be able to tell me how certain you are about your prediction. So I can use their certainty or their estimation of their probability to weight higher or lower that classifier when I'm combining multiple of them together into an ensemble, right? So that's one of the uses of these kinds of estimations of certainty or estimations of class probabilities for ensembles. I might have one ensemble that does really well for a particular kind of portion of the sample space, so it would have high certainty. So if I'm using their estimate of the class probabilities, you can often improve the performance of your ensemble by taking into account whether they're certain or less certain in their estimates. Okay, so I'm gonna that's all we'll cover today. So I'll leave the rest of it for Thursday. So we've got just a little bit more to talk about. Maybe a few more details on the card algorithm, and I guess maybe the most important stuff we'll talk about on Thursday is a little bit about the other kinds of parameters that you can do with scikit-learn besides max depth in order to regularize decision tree. But we'll talk about that on Thursday, and I'll also bring up the assignment for the first time and get started discussing our next assignment 5 here. All right, yeah, so that's it. I'll go ahead and stop there.